This video presents Quizy Rider, how head movements influence motion sickness in passenger use of head-mounted displays. This work is conducted by me. Hi everyone, I'm Jing Li, together with Agnes Reda and Andreas Booth from LMU Munich Media Informatics Group. In self-driving cars, the driver will spend more time on non-driving related activities. Similar to a rear seat passenger today, the driver can use multiple mounted displays or even mobile head-mounted displays in virtual reality to have a video call on the way. A wider head motion range can increase engagement in such activities, but might also amplify the risk of motion sickness while switching between displays. Therefore, we aim to quantify optimal head movement for a good trade-off between motion sickness and the feeling of engagement in passenger activities. We designed a head gaze-based dwell-time interaction in VR HMD along the horizontal and vertical axis. Based on the frequency of 0.2 Hz tested in prior work, we investigated three head motion ranges: 25 degrees, 50 degrees, and 65 degrees with their calculated speeds, two orientations, pitch and yaw axis, and three durations of dwell time: 0.3 second, 1 second, and 3 seconds. Here is an example of a passenger performing the 50-degree head movement along the y and x axis, using 1 second dwell time to hit the red targets. In Unity, we implemented a virtual display with a cross shape located at a distance of 2.05 meters. The display shows the content of a moving low-poly bird to guide the passenger's head movement and a hover area with an identical size of the red square target. We chose a 4.4-kilometer city highway with relatively controlled traffic conditions and a good road quality. The main test route was an almost straight road for about 5 minutes of driving. The experimenter controlled the driving style with a constant speed of 80 km per hour in a Toyota Yaris hybrid, and performed no stops in between. For the HMD task, we used the Oculus Quest, a consumer-grade standalone VR headset. We tracked passenger head movement via the headset. We mapped the left-hand controller to the real-time car movement and synchronously subtracted it from the rotation of the VR headset. We planned this study using a within-subject design. In total, we invited 21 participants to the study, 12 men and 9 women with a mean age of 27.4 years and a mean MSSQ raw score of 12.6. Most of them, like 17 people, had no or rare prior VR experience. Before the global pandemic, 12 people traveled regularly as a passenger weekly, and 10 people have a frequent trip length from 30 minutes to 1 hour. In the car, the participants were introduced to our hygiene concept and study procedure, followed by a demographic questionnaire. They were then instructed to put on the ECG respiratory band to record the baseline data for 5 minutes. In a 5-minute trial round while the car was parked, they were asked to wear the headset and familiarize themselves with hitting targets in their central views. After checking seat belts, the experimenter drove the participant towards the city highway. Upon instruction, the participant put on the HMD again and continued the next condition. They experienced 3 dwell time durations with each pair appearing 8 times in a randomized order. When the participant ended a condition and took off the headset, the experimenter exited the highway, parked the car, and recorded the ECG data in a stationary environment. Meanwhile, the participants filled out the questionnaires. The procedure was repeated for the remaining range conditions. After this, the experimenter conducted a semi-structured interview. The entire study took about 100 minutes. While performing the HMD tasks, participants accelerated their head movements as the range widened. In comparison, they completed the task with a minimum deviation of 0.06 second and 0.04 meter per second in condition B. Participants performed best in condition B with the least deviation in the calculated time and speed. However, their voluntary movements imply a demanded range from their central views smaller than 25 degrees on the y-axis and 25 to 50 degrees on the x-axis. Repeated measures ANOVA test revealed significant differences in heart rate variability. Post-hoc testing reveals that RMSSD decreased significantly after the participants put on the HMD. High values of the stress index and low values of the RMSSD in condition A signals mental stress and motion sickness. Participants reported more severe motion sickness with a higher total score in a wider range of head movements. However, an ANDOVA test found no significance. Overall, our participants reported a moderately to highly comfortable and engaging experience with a low level of motion sickness across head motion ranges and orientations. Participants found the y-axis overall less comfortable in condition C, where they also felt more motion sickness in comparison to condition A. ANOVA tests showed significant differences in these two reports. Besides, we found overall moderate to high engagement across conditions. Participants also felt moderately present in the virtual environment. In addition, we found descending trends in the ratings of the pragmatic quality and the concentration, as the head movement range increased from condition A, B to C. ANOVA test revealed significance in the pragmatic quality across ranges. During the interview, participants reported cumulative feelings of discomfort after the ride, such as I didn't feel any sickness during the VR experience, but I felt motion sick after taking off the headset. Participants assessed the yaw movement more positively than the pitch axis. 9 people found the yaw movement easy and more natural, while 3 described the pitch movement uncomfortable and had to move the body to reach the target. Furthermore, 5 people bumped into the car ceiling or the side door in condition C. This wider head movement made them aware of the real world and decreased the feeling of presence. They reported that when I crashed into the car roof, I didn't feel engaged, as well as looking up and down made me feel the weight of the HMD. Participants preferred 0.3 second and 1 second. Our results from this head gaze-based task in a mobile field study, along with prior VR studies suggesting 1 second or less for simple tasks. Condition B performed moderately well in both physiological and subjective measurements, which we consider the best trade-off between motion sickness and engagement. Thus, we propose to design the main interaction area within plus-minus 50 degrees along the x and y axis. Based on the detected real-time performance of the passenger's head movements, the UI could trigger a guidance mode. The user can follow the emergent visual motion cues in the peripheral area synchronized with the real-time car movements. Therefore, we propose to design the UIs beyond the activities and consider the visual cues to guide the passenger's head movements for counteracting motion sickness. Faced with the upcoming concept of self-driving car sickness, future research will probably address large and multiple displays built into cars or brought in HMDs. Our automotive virtual field study approach may be a future research direction for investigating motion sickness in real-seat HMD usage. In this field study, we used an accessible VR HMD with specific technical parameters. A new model with a wider field of view and higher resolution might improve the user's visual perception and further influence our results. Future work can replicate the study with newer headset models. Faced with the challenge of balancing an effective elicitation of motion sickness while ensuring our participants' safety, we pre-screened for vulnerable passengers and thus limited and screwed our sample. We call for investigation on passengers with a high proneness to motion sickness in future studies. Out of safety concerns, we selected a city highway with relatively controlled traffic conditions in comparison to stop-and-go traffic on urban streets. Our results are therefore limited to such a traffic environment. We call for future studies on dynamic traffic conditions. Moreover, our current VR prototype achieved only a moderate level of presence across groups. Future studies can explore the design of the head gaze targets embedded into the virtual environment to enhance the presence. Different from the implemented discrete level of head range, we plan for a continuous head motion in a follow-up study to lift restrictions on the freedom of head movement in reality. Future studies can explore more sensitive physiological measurements of motion sickness to improve the study validity by controlling the potential impact of physical activity. To conclude, based on the recorded physiological and subjective data, we found a good trade-off for rear-seat passenger head movement, characterized by the range of plus-minus 50 degrees with a speed of 1.95 meters per second, a preferred motion around the yaw axis, and a dwell time duration of 1 second. Thank you very much.